All right, so here we are at our friend number 16. Notice our limit is back to a number, so we need to just try hammering that number in. So let's see, 1 squared minus 1. 1 times 1 is 1, minus 1 minus 2. So that's going to be negative 2. And over 1 minus 1, so this is going to be negative 2 over 0. Sad face, factor, 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 factor. All right, so we need two numbers that multiply to be negative 2 but add to be negative 1. So we have x minus 2 times x plus 1 over x minus 1. In this case, once we factor, we see that nothing cancels out. Therefore, we have to stick with this guy up here, and our limit does not exist because of that thing. Okay, so limit doesn't exist for number 17, not a thing. Okay. All right, so using your own words, explain the epsilon delta formula limit. I'll tell you my words. So for me, the epsilon delta form of a limit is saying that for some range epsilon around L, around our limit L, there exists some delta such that if we pick a number between x minus delta and x plus delta, we're guaranteed to get a number within that range around L. Okay, just in case that went a little too fast, I'll say it again. All right, so for some range epsilon around L, there exists some delta such that if we pick a number between x minus delta and x plus delta, we're guaranteed to get a number within that range. So we're trying to sort of figure out and hammer down specifically what these ranges have to be. Epsilon and then delta based on epsilon. So let's take a look at what this looks like trying to find delta in terms of epsilon. So delta in terms of epsilon. This is like what we've been doing the past couple days. So again, we take a look and we get this thing and subtract our 20 from both sides. So we get x squared plus 7x minus 18. Absolute value bars around each side. And we set that thing less than or equal to, or less than our epsilon. Set that less than our epsilon. So now what we do is we keep simplifying the inside of our absolute value bars as much as possible. So we need two numbers that multiply to be negative 18 but add to 7. So we get x plus 9 and x minus 2. This would be a good time to mention the thing that I completely skipped over. Remember that because we're looking for x approaches 2, our goal is always to get somewhere where x minus whatever our limit's approaching, in this case it's 2, so we want to get x minus 2 in the middle of our absolute value block. So we have this absolute value is going to be less than epsilon. We've factored all of the things. So we have to say, okay, which one do I care about? Which one do I want to keep? So I want to keep this one because, again, it leads back to our goal. So we're going to look at a way to get rid of this guy. To do that, we pick a range around our limit value. So 2 is our limit, and then we want to pick a little bit on either side. We're going to say, all right, delta is at most this. We're going to say, all right, so delta is, we want to go 1 on either direction. So we're going to subtract 1 and add 1 from 2, so we get down to 1 and 3. That is our range, our definition for x, of course. So that is our definition for x. X is going to be between 1 and 3. Or our delta is going to be between 1 and 3. So now we want to take these guys and see if we can figure out some way or what the biggest value of x plus 9 is going to be. Well, if we do that, our biggest value is going to be when we use 3. So then that becomes 12. So then we have x plus 9 is always going to be less than or greater than, no, less than, write the less than symbol. Less than or equal to 12, because the biggest x can be is 3. So x plus 9 is going to be less than or equal to 12, so we can take that 12 and substitute it in for x plus 9. So we have 12 times x minus 2 is going to be less than our epsilon. Okay, so now we break our epsilon out of or our middle part out of the absolute value brackets. Negative epsilon is less than 12 times x minus 2, and that's less than our epsilon as well. Divide everything by 12, and hey, look, we get to our goal. So we have negative epsilon over 12 is less than x minus 2, which is less than epsilon over 12. Putting that guy, oh, I think I broke it. Guys, I think I killed it. Are we still recording? I think we're still recording. Whew, whew, that was close. All right, so actually click the extend page button, Mr. Seja. So good. Okay, so we now want to put this back into our absolute value. So we have absolute value x minus 2 is less than epsilon over 12. And the reason we're allowed to do that is because this guy and this guy are opposites of each other. So once we do that, we then can say, okay, there was my goal. I have achieved my goal. So now delta is equal to epsilon over 12. Oops, that's a 3. That's not an epsilon. Epsilon over 12 is going to be part of it. But we have to ask ourselves, did we pick a value? Did we get rid of a factor at some point? And we did. We got rid of the x plus 9 by saying, all right, I'm going to limit epsilon or delta to 1. So it's going to be, delta is going to be the minimum of these guys. So whichever one ends up being smaller, that's the one we're going to pick for our delta. Okay, cool. On to number 3 of page 3. So here's number 3 of page 3. Has the same instructions as number 2. We want to find delta in terms of epsilon. All right, so first step, just like always, we want to get this guy over to this side. So subtracting 23 from both sides gives us negative 6x minus 18. And that's less than our epsilon. Now's a good time to remind ourselves of our goal. Again, we want to get to x minus whatever our limit is. In this case, we're approaching negative 3. So x minus minus 3, it can probably much more easily be rewritten as x plus 3. That's our goal. That's what we're trying to get to. Okay, so from here, we want to simplify our thing inside the radical as much as possible. If we want, we can factor it. Maybe that might be a thing. Let's maybe just do that. So we factor out a negative 6 times x plus 3. And hey, look at that. There's our goal thing. There's what we're trying to get to. Negative 6 times x plus 3 is less than epsilon. So we, again, break our absolute value thing out of the prism. We break our absolute value guys out of the prism. And we say, all right, negative epsilon is less than negative 6 times x plus 3, which is less than epsilon. Okay, we divide both sides by negative 6. And remember, whenever you divide by a negative number, these guys need to change. So we get epsilon over 6, because negative divided by a negative is a positive, is greater than x plus 3, which is less than, or which is greater than, excuse me, negative epsilon over 6. Okay. So then we have this guy right here and this guy right here, which are opposites of each other, so we can put it back in the absolute value prism, and we get epsilon over 6 is less than, or is greater than, the absolute value of x plus 3. Because we have our goal in our absolute value bar, we can now say that delta is equal to epsilon over 6. And that is our range. We don't need to do the minimum thing because we didn't, at no point did we, in our entire solution part, at no point do we have to say, okay, I'm getting rid of a factor by making a choice and making a distinction on epsilon. Okay, we didn't have to do that, so we're not going to worry about it. All right, so on to page 4. All right, so here we are on page 4, number 4. Using your own words, explain the intermediate value theorem. So here's what the intermediate value theorem is. Essentially, it says, if our graph is continuous between 2 points, if our graph is continuous between 2 points, then for every y in between the y values of those 2 points, there has to be some x in between the two x values of those points that gives us every single one of those y values in between those points. Okay, let me say that one more time. If our graph is continuous between 2 points, then for every y value in between those 2 points, so in between the y values of each of those points, there has to be at least one x value in between those 2 points that guarantees that y to exist, that when we plug it into our function, it will exist. Okay. The types of questions I'm going to ask are going to be a little bit different than the ones that's in the worded on here. So I'll be sure to change the wording when we get to numbers 5 and 6. All right, so I'll ask this question a little bit different. Essentially, it'll say, all right, so we have this function right here. I'll give you a function, and I'll say, um, I'll give you a function, and I'll ask you, so is there some value x between 0 and 4 such that there has to be a -7 between those two? Okay? So the way we evaluate that is, so let me restate that one more time. So I'll give you a function, and I'll say, on this function, is there some value between x equals 0 and x equals 4 such that y is -7? Okay? Is there some function, is there some value between 0 and 4 such that we have to have a 7? And the way we check that is we say, okay, I evaluate my function at the lower limit, so the lower x, the smaller x. F of 0 is 0 squared minus 16, which is -16. So that's our y value and our x. So we have the point 0, 16. So we have 0, 16. We have some point up here. And then at 4, so we evaluate our function at 4. So that's 4 squared minus 16, which is 16 minus 16, which is 0. So at x equals 4, then there, oh, sorry, that's a -16, not a +16. Come with me. Whoop. So now my question is there some value of x in between here, x equals 0, and here, x equals 4, such that there has to be a -7? Okay, so can I connect from this point to this point without having some x value that gives me -7? And in this case, no, I can't. So there does have to be a -7 in between. There does have to be a -7 in between those two, in between here and here. Okay? So let's move on to number 6. All right, here we are with number 6 on page 4. Again, my question would be, is there a value of x such that y would have to be 12? So does that y exist between the 2 points? So again, we're going to evaluate f of -3 equals 3 squared plus 3 times 3 minus 16. And that's going to be 9 plus, or -3. Whoopsie daisies. 9 minus 16, so that's -16. And f of 4 is going to be 4 squared plus 3 times 4 minus 16, in which case this is 16 minus 16 plus 12, so that is +12. So is there some x in between -3 and 4 such that the f evaluated at that number is going to be -12? And because 12, or excuse me, -12 is in between these two things, yes, there is. Yes, there is a -12 between blah, 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 between words, between -3 and 4. So another way I might ask something like this would be like this. All right, so let's pretend like that doesn't exist. And let's pretend I didn't ask you for between -3 and 4. Let's say that I asked you about something between -3 and 0. Okay? So again, and I'm going to say, is there a 0? Is there a 0 on there? So is there some value that makes y equal to 0? Okay? Is there a 0 on that interval? Same thing, we evaluate f of -3. We did that, and that was -16. And then we say, all right, what's f of 0? Well, that is 0 squared plus 3 times 0 minus 16, and that is -16 as well. So what that is saying is because 0 is not in between those two, we can't say for certain whether or not that thing exists, whether there is a 0 in between -3 and 0. There might be, there might not be, we don't know. So that is unknowable with the intermediate value theorem. Okay, we can't figure that out with the intermediate value theorem. Okay, so I hope that helps with the intermediate value theorem idea. So that's number 6. And I think I've got 1 or 2 more things. We haven't talked about the squeeze theorem or anything like that. So we're going to move on and talk about some of that stuff. We also haven't talked about loss of significance errors. Okay, so I'm going to ask you a loss of significance error type question, and this is how it's going to look. I'm going to give you some limit as x generally approaches infinity, or some number, either way. But as x approaches something, and I'm going to ask you to use either a graph or a table to estimate what you think the limit is going to end up being. In the table, I want you to demonstrate a loss of significance error, and then I want you to fix it. And then I'm going to do that, I'm going to say, rewrite the function to eliminate the loss of significance error. Essentially math to make it not a loss of significance error anymore. Okay, so in order to do that, we're going to go and set up a table. Again, this is our same function. Sorry about the word infinity instead of the little symbol. I couldn't make my computer do it, and I didn't feel like taking the time to, copy paste all that sort of stuff. So if we take this function right here, and we plug it into our calculating machine, and then we say, okay, I'm going to say x is 10. So it's going to plug in, then we plug in 10 for all those x's, again, using the store command. That'll be huge. If we plug in 10, we're going to find that our y is going to be something like 3.99 and 3.999 and go. All right, so 3.999 and a bunch of stuff. Now if you change x and make it into 100, well, y is going to end up being 4. Then if we go to 1,000, y is going to be 4 again. So I think we can safely assume that for part A, our limit as x approaches infinity is going to be probably in the 4 ballpark. Okay, so we can make that assumption. Then, if we keep going, we plug in 10,000. Okay, our calculator breaks. Okay, it can't handle that. This right here is the loss of significance error. So this is part B. That's part B. That loss of significance error, you need to show me that in a table. You may have to go a ways, but I promise you, whatever I give you will break. I can break calculators, all right? It's something I'm good at. I can break them, all right? So that's part B. So then part C is going to say fix it. So part C, that is not even close to a C. That's a number 5. So then part C is going to say fix it. So we take this, x squared, and then times square root x to the 4th plus 8, and then that thing minus x squared. We want to multiply this by its conjugate. That's generally going to be our fix. If we can just algebra it out, then we might want to do that. But multiplying by the conjugate is generally going to be our fix. So we're going to go ahead and multiply by square root x to the 4th plus 8. Sorry, I'm running out of room. X to the 4th plus 8. And then for our conjugate, we're going to change the sign in between the first term and the second term. So that becomes x to the 4th plus 8 plus x squared. So we multiply these things out. X squared is going to come along for the ride. Times the x to the 4th plus 8 and the x to the fourth plus 8, they multiply together and they cancel out their squares, so that's x to the fourth plus 8. Then x to the fourth plus 8 times x squared is, let's see, plus x squared times x to the fourth plus 8, and then minus x squared times the square root of x to the fourth plus 8. And then now we multiply these last two guys, so we end up with minus x to the fourth. Okay, sorry, ran out of room. So now what we want to do is start looking for stuff that goes away. Well, this x to the fourth, this negative x to the fourth, and this positive x to the fourth goes away. Oh, that's super embarrassing. I'll fix it here in a second. The x and the negative x squared times x to the fourth plus 8, those go away. So we're left with x squared plus 8. But I forgot to do something hugely important. We can't just multiply the top by something. That just changes the problem and makes it, makes our life a lot easier. We have to multiply by 1. So again, the denominator also has to be, come on, smartboard, work with me. Square root of x to the fourth plus 8 plus x squared times 1. That's going to be x to the fourth, or square root of x to the fourth plus 8 plus x squared. Okay, so this, or no, not x to the fourth plus, not x squared plus 8. Oh, wow. Kids, don't do math when you're sleepy, unless you're in math class and then you kind of have to, but whatever. That just made it worse. Come on. All right, there we go. Okay, come on. And fixed it. Wonderful. Now let's make an actual line that goes above the thing. Here we should have multiplied x squared and 8, so that should be 8x squared. So this is our fix for part C. Hopefully you were able to figure out through all of my shenanigans how to actually do this. It's all there. It just was not in the best order, and I apologize for that. Okay, so with that, I will do one more thing talking about the squeeze theorem, and then we will call it a day. Okay, so here's our squeeze theorem. I will ask you a question like this up here, where it says limit as x approaches 0 of this gross thing. We want to evaluate that using the squeeze theorem. And we want to take into account some bit of knowledge. So I will generally give you this step. This is the first step. So we have the limit part that's attached to our problem. And then I'll say, given that we know blah, whatever that blah is, that's this guy right here. So this is where we want to start. So our goal is to get this middle part to match up with what we started with. We want to get that to look like that up here. So what we need to do is we need to go in order of operations and try and get that middle part to look like the top. So we want to look at for parentheses, exponents, any of that sort of stuff before we start trying to add and subtract, multiply and divide. Okay? So let's multiply first. Let's multiply first because that's the first thing that happens. So we need to multiply this entire thing by x squared. So we have negative x squared is less than or equal to x squared sine of 1 over x, which is less than x squared. Okay. So from there, we want to incorporate that adding 4. So we're going to go ahead and add 4 to everything. So we have negative x squared plus 4 is less than or equal to x squared sine of 1 over x plus 4, which is less than or equal to x squared plus 4. So now we want to take and apply our limit as x approaches 0 to these two end pieces. So our limit as x approaches 0 of this guy, well, it's just a polynomial. We plug in 0 for x, and we get that is 4. Less than or equal to limit x approaches 0 of x squared sine 1 over x plus 4 less than or equal to, our limit of this guy over here is again going to be 0 squared, which is 0, plus 4, which is 4. So because our limit has to be between 4 and 4, the only number that's in between 4 and 4 is just 4. So this whole thing equals 4. Okay, so that's our limit. Cool. All right, that does it for the test review. Um, I was going to do a quiz review, but I did all the stuff that was on your quiz. So if stuff still isn't clear about your quiz, find me on Monday, okay, and we'll talk about it. All right? So from there, I bid you adieu. Have a fantastic weekend. I love you all, and I will see you all on Monday. Okay, bye.